Welcome to the video presentation of our SIGCHI 2024 publication. In Kinetic Signatures, a systematic investigation of movement-based user identification in virtual reality, my colleagues and I investigated biometric user identification in VR, particularly through kinetic signatures and how they can be designed to increase identifiability and thus system security. Virtual reality head-mounted displays need to know who the user truly is that is using them. This is necessary to personalize the device and to enable information security. However, most often pins and passwords are used for this purpose, which have dozens of shortcomings. For example, they are slow and clumsy to enter in VR, as shown in the video, being hard to memorize in general, and a bystander can easily observe an immersed VR user to steal their PIN, as shown in previous work. Therefore, new modalities for behavioral biometric user identification emerged within the last years. Those approaches use the user's kinetic signatures tracked by the headset for biometric user identification. A kinetic signature is the user's traces of their individual spatiotemporal body behavior that is suitable for behavioral biometric user identification. When a user moves during experiencing their virtual environment, they are being tracked by the head-mounted display and controllers. These traces are so unique and individual that they are suitable for biometric identification. Many researchers already investigated case studies and examples of kinetic signatures in VR. These investigations range from throwing virtual balls to grabbing, pointing and walking, or engaging in games such as archery and bowling. However, one central piece of knowledge is missing so far. What makes these VR activities suitable for identifying users? How are all those different body movements related to each other? Why is one movement more identifiable than the other? So, the motivation for our work is to understand what contributes to the identifiability of kinetic signatures. Therefore, we checked literature on human physiology and biomechanics and found that muscle movements are of isotonic or isometric nature. The muscle activity then defines how joints move, resulting in the end, for example, in the movement of an arm. Here we see an example of an isotonic muscle contraction. On the left-hand side, the muscle performs a concentric contraction. This leads to the arm moving upwards. On the right-hand side, the muscle elongates through an eccentric contraction. This leads to the arm moving downwards. The interplay of concentric and eccentric muscle contractions is called an isotonic contraction and defines much of our body movements. However, muscles can also perform an isometric contraction. This muscle contraction exerts force, but the joint is not moving. That is necessary to hold the arm still, for example, when carrying a heavy object, so the muscle is working, but as a result, the arm is not moving. Checking literature, we found a well-established classification of sports proposed by Mitchell and colleagues. In their classification, they propose classifying sports by their inherent degree of isometric and isotonic movements. Isometric movements correspond to static movements, and isotonic movements correspond to dynamic movements. So, for example, a sport, such as tennis, differs from bowling by its degree of dynamic movement components. We simplified Mitchell's space into a 2x2 matrix based on their extrema and picked sports to investigate in VR, marked in bold. This leads to our overarching research question, which is how the static and dynamic movement components influence a kinetic signature's identifiability. We furthermore proposed two hypotheses. H1 states that high dynamic is better than low dynamic during B, sports, but also during A, self-exercises. On the other hand, H2 states that high static movements are inferior to low static movements for identifiability during sports and self-exercises. While the existing classification covers only sports, we also wanted to investigate the same type of body movements in a non-sport context. The reason is that such sports always come with a certain set of rules. For example, in tennis, you always hold a racket and run towards the tennis ball, thus the activity defines how the movement should be executed. Essentially, we also wanted to investigate kinetic signatures at its core and remove the specifics imposed by sports. Therefore, we opted for bodyweight self-exercises that are performed in place. We teamed up with the head of university sports, who is a sports scientist, to design bodyweight exercises through creating levels in the commercial O-shape application. However, it must be noted that we did not seek to compare between sports and self-exercises. Therefore, we explore our hypothesis within sports and within self-exercises. In sum, we choose static and dynamic as our independent variables with two levels, high and low, and as a dependent variable the identifiability denoted by the recall rate. During the exercises, participants engaged in the O-shape application. They needed to perform varying degrees of static and dynamic movements to fit through virtual walls and to collect virtual coins. During the sport games, participants essentially engaged in the corresponding game following the respective rule set. As a result, we collected a variety of 8 different sets of kinetic signatures, 4 for the self-exercises and 4 for the 4 different sports. To collect these kinetic signatures, we used a MetaQuest 2 HMD and AirLink. We implemented a multi-purpose, manually operated logger that can log any VR application on the PC that implements the OpenVR interface. For this reason, we always had 2 experimenters present in our study, where one operated the logger and the other conducted the procedure. We acquired O-Shape as an application for self-exercises and 4 other games on Steam for the sports. Our logger source code and dataset are available online. We invited 24 volunteers following a power analysis for repeated measures ANOVA with our study design. 7 of our participants identified as female and 17 as male. They were close to 27 years old at average and had a low to medium VR experience. Our user study followed a within-subject design with a repetition session after 1 week. Therefore, we re-invited the same participants to proceed through the same procedure 1 week later again. Our study design had 2 blocks, where participants engaged first in the self-exercises and then the sports. We counterbalanced the conditions per block, and participants engaged 3 minutes per condition, but could test it out for 1 minute first at every time. As a result, we obtained a fully balanced design and dataset. To create a deep learning-based user identification system, we first benchmarked 11 deep learning model architectures proposed by Favas et al. We performed a holdout validation and exclusively used the data of the first session for training and second session for testing. As best models, we find the fully connected network in sports that has an average accuracy of close to 75% and the inception network for the self-exercises at close to 72%. The best conditions performed at over 90% accuracy respectively. We choose these networks for the corresponding blocks of the study. For pre-processing the data, we first resampled it to 60 Hz as our logger sampled faster than the HMD, min-max normalized the data, applied a zero-based pre-padding and set all positions relative to the start. We then conducted a repeated measures analysis of variance for the self-exercises. Here we applied the ART procedure since our recall rates are not normally distributed as indicated by a Shapiro-Wilk test. Here we only find a significant main effect for the dynamic movement component, meaning that high dynamic yields higher identifiability than low dynamic, supporting hypothesis 1a. However, we did not find any significant differences for the static main effect and interaction effect, thus hypothesis 2a is not supported, albeit the underlying data followed a supporting trend for the main effect. For the VR sports, we again find that we have not normally distributed data. After applying the ART procedure, we find significant main effects for both the influences of static and dynamic movement components. They supported the hypothesis 2b and 1b respectively. Furthermore, we also find a significant interaction effect between static and dynamic. Here, 5 out of 6 contrast tests are significant following Holmes' correction. Summarizing, we see that hypothesis 1b and hypothesis 2b are mostly supported with 2 exceptions. First, we did not find significant differences in the comparison between low static high dynamic and low static low dynamic. Moreover, high static high dynamic was lower than low static low dynamic, which supports hypothesis 2b but opposes hypothesis 1b. However, it must be noted that these 2 hypotheses are mutually exclusive for this specific contrast test. We believe that in the interaction, the influence of static outweighs dynamic, since its eta square p-value is approximately twice as large. We furthermore wondered how participants experienced sports and self-exercises. During the study, we asked them for their workload with the raw NASA TLX questionnaire. All in all, their order of conditions within each block was ranked identically in sports and self-exercises. Overall, we can also accept hypothesis 1 that high dynamic is better than low dynamic, since we found evidence in sports and self-exercises. Yet, it needs to be noted that a moderation throughout the interaction effect can take place in sports. Moreover, we can accept hypothesis 2b, but we did not find significant evidence for hypothesis 2a. Therefore, we cannot universally accept H2. We also saw in the interaction that low static is most important, outweighing a high dynamic degree of movement components. We furthermore found patterns of our hypothesis in previous work, but must also state that these are specific to the VR context. Particularly, isometric movements are different in VR due to the inherent restrictions of imposing weight feedback to users compared to the real world. To design kinetic signatures with high identifiability, it is most important that they have a low static movement component. A high dynamic movement component is also very beneficial. These principles are ideally employed in an implicit user identification interaction. Kinetic signatures are not meant as drop-in replacement for passwords. Instead, an application can sample them when they naturally happen anyways. Then the user can be identified without realizing, and it fully relieves them of the burden associated with today's authentication mechanisms. Thank you for your attention.